folks, I don't even mean to jump in. I'm just saying this is fantastic. So we were rolling right into the panel, and we'd just like to invite other speakers that were in the workshop to join, and we can continue this discussion. And we have a few other seeded questions that we're ready with, but if the panelists would like to continue on this front, we're happy to do so as well. Unfortunately, we also had Professor Hadass Kreskazet, who was going to join us today, but she was pulled away at the last minute, so she won't be here with us. But those who are here, we're delighted to have you to continue the discussion. So if there's no further questions about this, or chatter on this particular topic, we'll actually maybe go back to the learning item as the first item we seeded, and we're going to try doing one quick thing. We're going to try doing a quick poll. So I'll read out the seeded panel discussion that we secretly sent to the panelists yesterday, just in advance, slightly in advance, just so there were no major surprises. Do we think, as a panel, we being you folks, that there's no need for research related to POGO systems? So much to, in the vein of what Gaurav was talking about, if we have learning systems that become more and more advanced, will AI just eventually tackle this inherently? And it's just something that'll get finished or become capable in the background? Or, so is that something you agree with, or do you think that actually we can't just leave it to AI blindly or learning blindly, that we actually have to do some manipulation of the systems and actually focus on this as a research topic? And we'll leave the poll open for just like another 20. Oh, it's good. We're getting lots of, getting some few. Seems like there's a popular, the poll is very skewed in one direction. All right, so it looks like one or two people are not sure. It's like about a portion of our audience disagrees that we actually thinks we should study power on and go systems specifically as a topic. And not too many agree that AI would just tackle it. So maybe I'll ask Valentine to end the poll in about 5 seconds. And if anybody has thoughts, feel free to chime in. Is AI is AI magic / learning? We'll call AI learning for the purpose of this discussion. If any panelist wants to tackle that.
Yeah, if I can start with maybe an easy comment here, or like, something that is a little bit going against the question itself, is that, your question is about, essentially data-driven, learning-based versus model-based approaches. But I think that is getting into a false dichotomy somehow. Like, I don't know why we're getting so much, like, on these, on the contrast between these two topics is like, saying planning versus perception, right? So it's a dichotomy that doesn't make too much sense. And I think part of it is that, of course, there is huge hype for deep learning, and now, like, deep learning systems are revolutionizing self-driving. But the truth is that all these systems have, of course, a number of, like, estimation blocks, a number of, like, blocks that are not data-driven. So I would say that the state of the art in this system is already a combination of learning-based and model-based blocks. So yeah, in that sense, I don't think that we have to, the question is not which one will win. I think the question is, how can we use what we learned so far on the model-based side of things to help, for example, training models with less data, make them more generalizable to other environments, which is really key to the POGO setup.
Okay, yeah, very fair. Anybody else have? I have one comment that I'll ask. I'll in response. I'm a moderator, so I'm not supposed to chime in with opinions, but I'll ask a question to the panel as well, which is, so is it a question maybe more of human expectations then? If we're talking about what's on the box, I have a reasonable number of students in some of my usually earlier stage classes that come in and say, well, let's just use deep learning end to end. I mean, why would we do anything else? And they're actually, sometimes they're actually upset that I say, well, there's logic. Why don't we, today we're going to talk about logic. Logic. It's this. It's a we can deduce things with logic, but can't you just use learning? And they don't, and I say, well, logic is actually part of AI, you know, and they say, but that's not deep learning. I don't, there's no Medium posts on this. Why are we learning this? And I go, and then I kind of sigh. So I'm wondering, maybe it's just, maybe the world is being sold the wrong expectations out of the box about the way these techniques operate.
I mean, if I can just add something to that, I think I'm also sighing. I hear the same thing also often, but I actually think that that there is a bit of a correction coming in, right? That we start to realize that while deep learning is an incredibly powerful tool, it can't just do everything, or well, maybe it can, but it is a matter of how long it takes to learn that thing that you want to learn. And I mean, we can probably say, I mean, we humans, we are examples that in some sense end-to-end learning works over millions of years and, you know, generations. It works. And so to me, then it comes down to data efficiency and nothing else. It sounds a bit, you know, profane in that sense. But if we want to build robots that work the same way as we do, well, we probably just simply don't have the time to do it in this kind of end-to-end way without any form of modularization and supervision and engineering. I mean, that's at least the way I see it at the moment. And I think we are somewhat converging towards that, as Luca said as well, right? That the current systems that seem to do best, they require a certain amount of engineering to really get this stuff to work. And so that's, yeah, then it becomes also more difficult, of course, our job. And I think it has to do a lot with how do we put these things together? What do we do about uncertainty, right? How do we understand, as Nathan was saying, how do we understand that we don't understand something, that we have never seen it? It's an out of distribution example. So, I mean, in some sense, I'm glad there's a lot of challenges for us in this context that we can still address.
Can I just add like one other point on that? I'm agreeing with everyone so far. I completely agree with that point. And yeah, I do agree also with Luca on this dichotomy, which is kind of like silly, like model-based versus data-driven. But it is kind of interesting to think about like how we can integrate like model-based and data-driven approaches and when we should integrate them. So I've recently been working with a few NLP people, and in their field, right, like a lot of things are solved by deep learning, and a lot of these models are just like deep learning based models that you're using off the shelf. And now that you're trying to do anything that's slightly more interesting, you're kind of stuck, because the best thing that's out there is this thing that's fully trained and is perfect, and we can't use a grammar-based model because that will not hit like the deep learning level, but there's no explanation, no understanding of how I can actually use this in like a visual question and answering problem or something that's slightly like more complicated. So I think we are not like as field of robotics, we're definitely not there yet, partly because we don't have as much data, right? Like we don't have that much interaction data, we are not very efficient. So we are taking a little bit of a more careful look at how to combine data-driven approaches and model-based approaches to do better, like do representation learning or bring in ideas around logic as we're training these data-driven models. And I think that is good, because maybe for some of our later problems, we'll have like a better way of understanding what goes in the system. And it's kind of interesting to see like the NLP field like being a little bit stuck right now with these models that they've trained and not being able to answer anything that is more interesting because they're stuck with this data-driven thing.
It's actually a very interesting and very interesting point you raised, Dorsa. Also, so I guess when we talk about models, if we talk about deep learning for now and interpretability, then we can go back to boxes and say that the box really has no writing on it telling you exactly what it does, to push the analogy a bit farther, in that sense that you kind of just get a box that has inputs and outputs and is hopefully doing what you want, but you cannot look inside it. So very interesting. Okay. All right. So, okay, false dichotomy, definitely. So yeah, we asked the question because it does tend to be a provocative one that people comment on, because you know, a certain group, also the media, I would say, does an excellent job of, in some respects, talking to people who are not necessarily roboticists and hyping things that then get taken sort of out of context and become expectations that are then not met. Perhaps self-driving is one example where it's just a really hard problem, and now we're getting there. But it's it's hard. It's just difficult, right? And everyone's had expectations of self-driving cars for many years, and we're still not quite there. So okay, so we'll leave that one for now, and we'll pop over to a second question, and I will hand over to Stefan to ask our second seed panel question.
Yeah, I wanted actually to follow on a little bit on some statements that Stefan, Leutenegger, Luca, and also Nathan made in terms of modeling and the parameters. So Stefan mentioned that we simply don't have time to learn things and data efficiency. Nathan talked about this unknowns, and that the model are very, very complex, so we just need a lot of data to learn it. And Luca told also about this, all these elements on bringing things together. And I think this is a question that we should really ask ourselves, is like power on and go system for really complex systems. The more complex we make them, the more capable they should be probably. But the additional complexity, it also adds more vulnerability. Right? So the more elements that you add, the more you need to test. Same thing as with an operating system, with software. The more complex it gets, the more difficult it is to actually test all the failure modes. And I think it's similar with the power on go system. So you add more sensors, you add more capabilities, but it's more and more difficult to actually test if there are any hidden elements that actually fail in your power on go scenario. So how do you see this trade-off, and also probably from a space applications view from Ali, right? So probably, I remember the discussions on the Mars Helicopter Scout where we debated on adding one sensor, and then everybody screamed, no, that's another failure potential, right? So this sensor can also fail. And we argued, no, we need that because we can then have a better estimation on our motion. And this was really the discussion. So also from a space applications point of view, you probably want to be the most simple possible, but still want to fulfill your capabilities. As Gaurav mentioned, the Mars rover is a classical example of a POGO system, and has quite a number of sensors, quite a number of failure points as well. How do you think about this trade-off on adding elements versus testability, certifiability at the end of the day of the overall system and failure points?
So if I can, I don't know if the question was for a specific panelist here, but if I can maybe break the ice here. It's very into, so like, I said that, we need a theory on how to put together things. And there is this intuition that putting together more modules, more capabilities is going to limit robustness and to increase complexity. However, I have to say that on the perception side, I'm not sure that's the case, in the sense that I was thinking like that. I was thinking like, more modules and more perception is going to lead to brittle systems. But the more I think about it, the more I think that if a robot is able to understand more aspects of the scene of reality, is going to be more robust to failures. For example, like, I'm talking in my slides about object detection in point clouds. If I ask you to detect an object in a point cloud, like in challenging condition will be very tough for a human to play with this point cloud and look at the object inside. But if I put this point cloud in a context, right, I put it in a scene, for humans it's much easier to really understand what's going on. So there is a lot of context that is being leveraged to improve the robustness of perception. You don't solve a perception task in isolation. You solve 10 different perception tasks. You sanity check that the result of these perception tasks are consistent with each other. So in that sense, I think there are opportunities in the sense that, if you get to this theory of robust systems, we have the potential to just see a radical change in the level of robustness of the systems that we can build, I think. And yeah, initial thoughts.
Yeah, a very quick couple of comments on that. I mean, I fully agree with what Luca was saying. I think definitely there is this gap for a theory of reliability or theory of robustness that somehow, you know, bridges the gap between these different modules. But I think on the way to develop that, I think one other thing, big thing, important thing is missing are metrics. I think just as important as how to develop those is to come up with testing framework that says here is the way that we test the robustness of the system. Here is a principled approach that if you propose an algorithm or if you propose a method, you know, we can check it against and say, you know, what it passes, what threshold it passes or not. And it's a hard problem. I don't think anyone has a good answer at JPL, you know, as big as, you know, we have this division for science and engineering, but almost the same size division just exists called assurance and reliability. I mean, it's a huge division with a lot of people, and their job is just, you know, come up with these metrics, come up with testing methods. And something we don't have in robotics in a formal way. We do all of it, you know, somehow in our labs, part of our resources goes into that, but it's not as big of a branch or formal branch that says, okay, these are just reliability people, or these are reliability sessions at conferences that just talk about testing methods and these frameworks. I think that's just one general comment that maybe we are missing as a community, as a theory. And number two, I would say, just a quick comment on putting more modules. I think, yes, it looks a bit scary, you know, from at the beginning, you know, complexity, but look at other similar fields that are older and more mature. Look at like analog circuit design, right? Every single transistor and all these are very complex, like a lot of challenges from every angle. But once you have good abstraction methods that you can, you know, test them, verify them, you build a module that encodes 10 different modules, but then that's it. That's a current mirror. You call that clock, but it works robustly, and you test it with certain things, and then you build another one and build another one, and then you have a chip that has billions and millions of transistors and extremely complex. You know, when you take a step back and look at the you know, individual elements, it's unbelievable how it works and how robust all our computers work. I think our field is just young, right? So we are gonna get there. I think all these ROS packages and all that, you know, are coming, but if we can just have a little bit better theory, better principled ways to put them together, test them, I think we are keep, you know, building, and then there will be much larger blocks, and then we will, you know, get closer and closer to what Gaurav was saying, that we will really, it will be a dream day that we all only concerned about activity planning, right? We say, okay, all these lower level things are robust and enough. We have tens of different calibration things but now let's think about autonomously. So the system looks at mission specification, task in hand, and say, okay, I need to grab these two calibration methods. I need to grab this type of Islam and all that, because given my mission specification and test elements, I know if I put these together, such and such theory will say I will satisfy specification with this level of, you know, chance or, but yeah, I think it's just we are a younger field in general.
So one thought sort of picking up on that is, you know, there's a sort of explainable AI is an old field, right? So the idea that you build systems that tell you something about how they work, right? It strikes me sometimes that one of the interesting things about if you're presented with a new system and you don't have the instruction manual, you don't get the proverbial box that tells you what it does. Can you develop a succinct description of how the system works in codes of small code length, basically? So I'll give you an example of what I mean, right? If you give like a 2-year-old a car, they can develop a theory of how cars work fairly quickly, right? I mean, 2 years are incredibly intelligent, obviously, so they can develop this theory because they're very smart and they build models of the world. But there's something about cars that allows you to give a 4-line description of how a car works, right? You know exactly what the steering wheel does, and you can express it to first order. You can express it absolutely perfectly just by saying, if you turn it to the right, the car goes to the right. If you turn it to the left, the car goes to the left. You know, if you press the gas, the car goes faster. If you press the brake, the car stops, right? And you don't need to be much older than 2.5, 3 years old to know that unless you put gas in the tank, the car doesn't go. Coupled with these 4 sentences, you have 99% of the behavior of this incredibly complex artifact captured in a code length which is very, very small, right? To some extent, I think when your field is mature, like Ali was saying, you have this ability, right? Robots are not there. You can't quite give a description like this of robots, right? I mean, to some extent you can. You tend to give it by analogy to other machines more than anything else. But you know, I think we'll sort of measure of success will be when we'll arrive at these sort of low complexity descriptors of systems level performance. I don't mean necessarily by 2-year-olds, but I just mean in our own minds. And it's a sort of a mark of how explainable the system is, how easy it is to infer its behavior. And how, even if it was built using black box techniques, how it exposes the right interfaces so that you can make inferences about its behavior that capture most of it. So I think that's a valuable property towards being POGO in some sense.
So that's a very interesting thought. But about what I'm also wondering myself is that that might also be related a little bit to the complexity of the task that POGO system is supposed to do, right? So a car in many ways is a very simple machine when driven by person in terms of the functionalities, not in terms of all the functionalities that there are, but in terms of the description you're mentioning. And if you're thinking about the more complex system, all of a sudden you cannot describe it, not even in an hour of talking about it. If you were to talk about what it is that the person does, a human, you might say it's a POGO system. You made the analogy earlier, right? But it is much harder to describe the human POGO system. So I wonder where robots sit and if we can ever get to that point. I mean, maybe with some robots, but I'm not so sure whether it's for all the robots that we are expected to build that we can ever get to that point. But we should obviously make an effort to make it to make them simple with their instructions. I agree.
And just to add on that, one more point is when we think about explanations, like I think it's a good question to ask who the explanation is for. Like, is it for the designer or is it for the user? And if it is for the user, a lot of times our explanations are actually made up. And people are very happy with made up explanations. Like they kind of like want to know what the system does. And when you're using like things like learning-based systems, if I have a vision system in this vehicle and it like doesn't detect the right thing because the neural net failed somehow, like I don't know what type of explanations like we can give there, or is there like any hope on like giving an explanation there?
I think it was neuron number 7 that failed. That's what I would say, or neuron number 3. Yeah, excellent points. Excellent points. If anybody, I'm just going to jump in with one, just maybe because we have about just about 10 minutes, a little bit less than 10 minutes left. We just wanted to ask one more, and just it's a great follow on, a great segue from what we were just discussing. It's the 5th seed question. We'll just jump ahead to that one for you folks, and that was related to what Ali just mentioned, and also Luca, Stefan. I'd love to hear what Arne also has to say about this from an industrial perspective. One of the things we put together when we wrote the workshop blurb was this problem of initial conditions being good enough. So somehow you have to get a good enough initial state, which maybe is calibration, is whatever. But one of the things we don't have now, and this is a question that's certainly not unique to us or this topic, is as a community, a framework for benchmarking or even quantitatively defining what we mean by, we literally just use the phrase good enough. And so the question is, which has been asked in many places, right? And if we have this kind of crisis, I would say, in robotics to some extent, how do you make benchmarks? How do you assess? I mean, there are very, very formal methods for assessing reliability, but are those applicable for all of the cases that we need to deal with? Are they too complicated? Are they not complicated enough? How do we actually go forward as a community so that I can even say to you, my POGO, whatever it is better than the POGO that you built in 2020. Now it's 2022, and my POGO robot it's approaching 0 on D and asymptoting to C goes to infinity much more quickly than your POGO robot. But you can actually, as Gaurav pointed out, you have this we have orthogonal axes, but the metric in that space is difficult to define. How would we actually do that? Does anybody have any thoughts? Even particularly from like an industrial standpoint, if you're working in industry and you need to sign off. Arne might have a thought on all of the hoops you have to jump through to get like ISO certification. I'm sure is an unpleasant prospect.
Yeah. In general, it's hard from the outside to understand the robustness of methods, and people make videos where they hit their robots, or I don't know, dim the lights a bit, and it proves that it still works. But from the outside, if you're looking at a huge set of conference papers and everyone is testing robustness in their own little ways, coming from as a research from industry, it's not clear where to start, what the best approach, what the most robust approach is. So it's definitely helpful to have some kind of standards for robustness, to be clear about these are the parameters that we care about being robust, and kicking the robot is probably not a good benchmark, but so just to be a bit more clear about the parameters you want to be robust against, and then test against these parameters. And then if I come from industrial application and be like, okay, we have problems with lighting here, let's look at this method because this is good under different lighting conditions. And this is sometimes hard to say from just looking at videos, because
yes, absolutely. Well, the videos where we kick the robots, the robots will watch those later and then come back to get us in 20 years once they realize we've been abusive. Okay, I will ask maybe one last provocative, I don't know if this is provocative or not, but maybe for some panelists will agree or disagree. Is it our job, should it be our job as roboticists to even define these standards for robustness, or should we leave it to people who actually don't know anything about, or on purpose don't know anything about or know very little about the underlying systems? Because then they're not biased, they're not inclined to ascribe greater or lesser capabilities. They just simply see what is and certify in that manner. Or would you say you actually need people that are technically educated in the area of robotics in order to come up with these types of metrics? Which means that we're going to actually it's going to take a lot longer, right? If potentially if we can't parallelize this process.
Mention 2 points on this. I think, yeah, there are pros and cons for either one, right? Like when we define benchmarks or rewards or things of that form, they're always a proxy, and then you optimize for that proxy. So you're not really robust, you're just optimizing for your definition of robustness. So it is good to have like some other mechanism or way or metric to check these things. But if you leave it to people who don't necessarily know how the underlying system works, then they might actually not know how it is going to fail either. And maybe they're then you need to think about how you're designing your test case scenario, as Ali was talking about earlier. We need to have formal ways of going about this robustness analysis. And that also introduces a lot of problems. I think pros and cons.
I think just to follow up on that, I think that both are important, right? At the system level, the product has to sell, right? So the product has to work for the end user. So I don't see a roboticist designing technical metrics, to make the person happy, so the non-expert, I think, should be in charge of assessing or in other words, I think the performance of the overall system is pretty easy to address, right? The system is designed for a specific function. Whether that works or not should be pretty clear. I think the responsibility for the roboticist is to understand that, again, the system is an interconnection of blocks. There are different abstractions, as Ali was mentioning, involved in these blocks. And the question is how to debug in isolation what's going on at every block in order to infer something about the behavior of the overall system. And I think understanding when the perception, what is the operational domain of the perception block, planning block, and so on, that should be the responsibility of the expert, I think. And I would say that, working in perception, I think that's tough. On the perception side is extremely tough, because already defining how to define, in which kind of environment my visual SLAM algorithm is going to work. I mean, you can get some proxy texture, you can get size of the scene, motion of the camera, but it easily gets intractable to get that description.
I think actually that's in many ways the main problem that we have, especially on sensing side of things, is that we cannot even define we cannot even define a process to go about robustness, because we cannot enumerate in any ways all the different things that can possibly go wrong. Right? This is I think the main problem. I mean, we can have our scenarios, we can make them harder, we can be as smart as we want. I think the main problem really is that there will always be a scenario that we didn't think about, and that quite likely our robot will fail in. So yeah, that's what I think the main issue is.
And to reinforce that, I think the main difference there with respect to planning and control is that in planning and control, you have a symbolic representation, which is typically very clear, right? So you have a state vector for control. The question becomes how to tolerate disturbance on the state vector or how to reach a desired vector. But for perception, really becomes a matter of representation. Like, what is the right representation of this room? So like, a bunch of points, a mesh, a volumetric grid, maybe representing the color of the walls. It's really like
just to even go further, so once you say you choose the representation, you will still have chosen a path to go from your sensory input to that representation. A bit similar as in your talk and my question, right? Then still things can go wrong in that process, right? So in some sense, you can never go around the sheer complexity of all the possible sensor measurements that you might get. There's no way around it. We can try to make progress, but at some point we are left with the complexity of the possible data.
I think it's wrong to assume that the power and go system must be absolutely failure-free. I think also like a complex system will never be failure-free, and the more complex it gets, the more failures it will make. Like my mobile phone, which does unpredictable things all the time. But I think these complex systems, if they should become power on the go, they must have a safe core, that it can fall back on. And if you have a complex visual reasoning system on top of a core that does what you expect, that might be totally fine. The robot might fail a few picks or whatever, but it can recover from that. It will not shut down, and it will not kill anyone. And I think this is what you want from a complex robotic system, not necessarily that it's absolutely 100% failure-proof.
Okay, very well said. Yeah, go ahead.
This goes maybe a little bit in contradiction to Ali's statement, right? So that we can certify building blocks, and then using these building blocks to build robust, very complex systems. I don't know, Ali, if I got several aspects wrong or like misunderstood anything, but could you clarify your thoughts to that last statements of Arne, or is?
Yeah, it's. I still believe. I think I still believe that's the only kind of way to go, right? I mean, at the end of the day, I don't think there is any magic, simple, elegant idea that's going to solve all the problems, right? At least I don't see it in other fields, right? When I look at more mature fields like power systems, like analog circuit design, or any other, even non-engineering fields, it looks like it's over many years. People have developed a lot of things. There was a lot of noise, but then the nuggets came out. Then a bunch of people came together, come up with very good metrics, and abstracted those. They became known. We have some of those tools now, like Kalman filter, right? It's came out of so much noise, probably in terms of different types of filtering and so on. But something that at the end, among everything, comes out and people say, okay, these are the metrics, and it works reasonably well. And it's not perfect. We know how bad it is in many situations, but it became the standard, right? So I think, so those exist in planning, control, LQG, Kalman filter, particle filter. So now I think we are at this stage, or as a community, that we are graduating from that and going to autonomy modules, right? Some basic, a little bit, more complex, that, okay, we are doing this small task or building a 3D mesh. Yeah, so I don't have a very good answer, but I don't also see a different way of going about it. And back to, tying it back to Luca's comment, I think, yes, on the perception side, those would be more difficult. But I mean, in general, perception is difficult, so testing will be difficult too. But I think there will be, again, ways to extract those, right? I can, again, you can imagine methods that, there are benchmarks that says, here are certain shapes or certain types of material, and any perception method that we develop, if it passes this set of standards and all these shapes and all that, we call it blah, blah, certified, 3D construction. And then over time, they grow, and then depending on the task, those blah, blahs will be picked, and the highest level of the task, I think, is, back to Jonathan's question, I think will be a joint work with the community, because that blah, blah will come from the sponsor or customer. I'll just give you an example. So with all this sub-T stuff, so we are getting some attention from mining community, for example. These guys come to us and ask, and then when they try to describe their final, product of what they want to see, you just discover a lot of things that you haven't thought about. It's important for them, but you haven't thought about, like their first concerns is, okay, I want this to be explosion tolerant, the mobility system and so on. So, but the point is, if let's say we have those hypothetical, like let's say perception modules with certain things, when they say, oh, I want to be able to do this in this much humidity or this much reflectivity of the surface with that level of texture, you can extract one of the modules and say, okay, this is it. With the computation level and the complexity level, I think this would be a good fit because this has passed this kind of test. And then, yeah, that's I think probably one possible potential way of going about this.
Yeah, I can make that even stronger, Ali. So I think that this theory of robust system that we have been mentioning in this workshop will do both what you say and what Arne was mentioning. I think in the sense that what you're saying is that a priori we compose these modules in a way that they do the job on a specific problem that you give them. But I think going to the point in which if you go out of this design envelope, they are going to fail. I think that this theory of robust system should also provide, will provide insights also for runtime verification and monitoring, right? Which is the way in which if you fail, at least you want to understand that you're failing and you want to take actions before before the failure at some module is cascading on failure of the entire system. So I think that this kind of system level theory will inform both, will confirm that you're confident in solving a specific set of problems, but it will also allow you to detect if you're working outside your design envelope. I'm not claiming I know how to do that, of course, it's another story.
There's already a paper in the works for this, actually. Okay,
actually, but it's very early steps. Yeah.
Excellent. Excellent.
Just a 10-second comment on that. I really very much like that. So basically, in addition to those tests, what it spits out that test, these are the failure points, right? So if you have those for modules, once you put them together, maybe you have some idea of what part of envelope you're not developing. And always you need to create a new module. Again, back to the analog circuit design, the same happens, right? So we have all these millions of modules, but the next modem Apple wants to put, the Qualcomm wants to build, they still have to go to their ADC, analog to digital converter, and change something to go out of the envelope and build a 5G after 4G, right? So that will happen, but at least they have basis. They say, okay, the rest exists. This is the module that needs to be improved so that the entire system works together coherently.
Very, very well said, Ali. Okay, excellent. I don't want us to take too much time, but this is a great discussion. Actually, I don't even want to end it. We keep going, but we should. We promised the RSS folks we would end right around 4:30, so we should probably try to do that. But delighted, and we'll thank all the panelists. One important thing I would just note at the very end is that humans are also imperfect, of course, and we've only looked at this question from a technical perspective. We do have a metric system of sorts for human performance, and that's the legal system. So when we get it wrong, someone gets sued, and the rules change. So in some sense, but as roboticists, I don't think we would want to build machines that have to go to court for legal. But anyways, so slightly different. So maybe we're holding ourselves to a slightly different standard than we're holding human beings. All right. So on that note, thanks. That's just my last word, edgewise. Panelists, thank you so much for taking the time.